Most people, if asked what holds civilization together, would point to governments, laws, or perhaps money. These answers are not wrong, but they are incomplete in ways that matter enormously. The real answer is infrastructure, not as a concept, but as four specific physical systems that operate continuously beneath everyday life, largely invisible until they stop working. These four systems are energy grids, water distribution networks, supply chains, and digital communications infrastructure. Everything else that modern society does depends on at least one of them, and most things depend on all four simultaneously. Understanding why these systems are so foundational requires looking past what they produce and focusing instead on what becomes impossible without them, because that list is longer than most people expect. Start with energy. The electrical grid is arguably the single most critical infrastructure system humans have ever built. Not because electricity is pleasant to have, but because nearly every other modern system requires it to function at all. Water treatment plants run on electricity. Fuel refineries run on electricity. Internet servers run on electricity. Hospitals, food storage, heating in cold climates, cooling in hot ones. All of it depends on a continuous, reliable supply of electrical power. At first, this seems obvious. Of course, things need power. But the dependency runs deeper than it appears on the surface. Most people think of a blackout as an inconvenience. Lights off, phones dying, maybe food spoiling in the refrigerator after a day or two. That framing captures maybe 15% of the actual consequence. The other 85% unfolds over days and weeks, not hours. And it does so in domains people rarely think about when the lights first go out. Consider hospitals. Emergency generators keep critical care functioning for roughly 72 hours in most facilities. After that, fuel resupply is necessary. Fuel resupply requires functioning logistics, which requires communication systems, which require electricity. The loop closes quickly. Now, zoom out for a moment. In a localized outage, fuel resupply happens because the surrounding region is still operational and can send resources inward. But in a wide area grid failure covering multiple states or provinces, that external support structure weakens significantly. The grid itself is not a single unified thing. It is actually several interconnected regional grids, each with its own generation sources, transmission corridors, and load balancing systems. When one section fails under stress, it can cascade. Cascade failures are the particular danger of highly interconnected systems. A cascade does not require a catastrophic initial event. It can begin with something relatively minor. A single high-voltage line sagging into a tree on a hot day, triggering a relay which trips a neighboring line, which overloads a third. This is not a hypothetical. It describes, broadly, the sequence that led to the 2003 Northeast blackout in North America, which affected roughly 55 million people across 8 states and a Canadian province within minutes. That event lasted about 2 days for most affected areas. 2 days was enough to disrupt water treatment in some municipalities, halt train operations, ground aircraft, close financial markets, and cause over $6 billion in economic damage. 2 days. Now ask what a 2-week version of the same event would produce, and the answers become significantly more serious. The reason energy sits at the top of this analysis is not just because so many systems depend on it, but because the energy grid has a particular vulnerability that other systems lack. Restarting it after a full collapse is genuinely difficult. Large power plants, particularly coal and nuclear facilities, cannot simply be switched back on from a cold state without electricity already present to run their startup systems. The grid needs power to restart itself. This is called the black start problem, and every grid operator maintains a small number of dedicated black start facilities, usually hydroelectric or gas peakers, precisely because of this. But those facilities are geographically limited, and restoring transmission across a wide area after a major failure takes days of coordinated technical work under the best conditions. Under degraded conditions, with communication systems also affected, it takes longer. This is the nature of the first system. Its failure does not stay within its own domain. It propagates outward into every other system almost immediately, which is why it functions as the foundation on which the other three rest. Move now to water. Clean water distribution is so normalized in developed countries that its engineering complexity is essentially invisible. Water flows from a tap. That seems simple. The infrastructure required to make it happen is anything but. Source water must be collected, usually from reservoirs, rivers, or aquifer wells. It must be pumped, using electricity, to treatment facilities. At those facilities, it undergoes chemical treatment, filtration, and testing. Then it is pumped again, using more electricity, into pressurized distribution networks that serve individual homes and buildings. At first, this seems like a straightforward industrial process, and in stable conditions it is. The complexity becomes visible only when one variable changes. Remove the electricity, and the pumps stop. Remove the chemicals, chlorine and other treatment compounds that must be regularly resupplied through logistics chains, and water quality degrades. Most people focus on the obvious impact of a water failure. No water for drinking, cooking, or hygiene. These are serious. A person can survive roughly 3 days without water under normal conditions. In heat, that window shortens considerably. But the overlooked secondary consequence of water system failure is sanitation. Modern sewage systems are also pressure dependent. When water pressure drops in distribution networks, it can affect the ability to flush waste through sewage infrastructure. In dense urban environments, the public health consequences of this begin within days, not weeks. Disease transmission increases. Hospitals, already stressed by power issues, face increased patient load. The two systems, energy and water, compound each other's failures in ways that are not always modeled clearly in public planning documents. Water also sits at the center of food production, agricultural irrigation, livestock watering, food processing and cleaning. All of it requires water in very large quantities delivered reliably. A 2-week disruption to water infrastructure in an agricultural region during a growing season can affect food supply for months afterward. long after the water system itself is restored. This is the nature of infrastructure cascades. The failure happens in one place in one moment, but the consequences arrive in a different place and a different time, which makes the causal connection harder for people to see and easier to underestimate. The third system is the supply chain. Unlike energy grids or water networks, supply chains are not a single physical infrastructure. They are a distributed web of relationships, contracts, transportation routes, inventory systems, and production schedules that together ensure a continuous flow of goods from where they are made to where they are needed. Modern supply chains are optimized for efficiency over resilience. That optimization choice has a specific name in logistics: just-in-time inventory. The idea is that holding large inventories of goods costs money, warehouse space, capital tied up in stock, potential waste from spoilage or obsolescence. So most systems have evolved to hold minimal stock and replenish frequently. This works extremely well under normal conditions. A grocery store in a major city does not warehouse 3 months of food in a back room. It receives deliveries multiple times per week from regional distribution centers, which themselves receive from national distribution hubs, which receive from producers. The average grocery store carries roughly 3 to 5 days of food inventory under normal shopping patterns. That window narrows to hours if purchasing behavior changes significantly, which it does very reliably at the first sign of instability. Most people focus on the obvious impact here: empty shelves, shortages of specific items, price increases. These are real and they are fast. But zoom out for a moment and look at what drives the supply chain beneath the grocery store level. Trucks move most goods in most developed economies. In the United States, roughly 70% of all freight tonnage moves by road. Trucks require diesel fuel. Diesel fuel is refined from crude oil at refineries that require electricity and chemical inputs. Those inputs arrive by pipeline or ship or truck. The fuel system is embedded inside the supply chain, the same way that supply chains are embedded inside the energy system. Everything loops back. Every system feeds into every other system at some point in the dependency chain. A disruption to the fuel supply does not just slow truck deliveries. It also slows the resupply of fuel to the trucks themselves, creating a feedback loop where the system's ability to recover from disruption is itself disrupted. Ports are another overlooked pressure point in global supply chains. Roughly 80% of global trade by volume moves by sea. The physical goods that stock stores, factories, and hospitals in most countries have passed through at least one major port on their journey. Port infrastructure, cranes, terminals, refrigerated storage, customs processing, is another energy-dependent, logistics-dependent system within the larger system. A significant slowdown at a major hub port, whether from labor action, infrastructure failure, security incident, or congestion, does not stay within the port. It radiates outward into production schedules, inventory levels, and retail availability over the following weeks and months. The global supply chain disruptions that followed the pandemic, years of 2020 through 2022, demonstrated this dynamic with unusual clarity and at a scale that most planning models had not anticipated. Those disruptions also revealed something important about consumer and corporate behavior. Both tend to respond to shortages by accelerating purchasing, which deepens the shortage, which triggers more accelerated purchasing. This is not irrational behavior. It is individually rational and collectively destabilizing. Understanding that pattern is important for anticipating how a supply chain stress event actually unfolds in practice. Now, come to the fourth system: digital communications infrastructure. This one is perhaps the most recently critical of the four, and also the one whose importance is most systematically underestimated. 30 years ago, a failure of digital communications would have been a serious economic disruption, but not an existential threat to the functioning of civilization. Today, the calculus has changed because the other three systems now depend on digital infrastructure to operate. Power grids are managed through digital SCADA systems, supervisory control and data acquisition networks that monitor and control the thousands of switches, relays, and generation assets that keep the grid balanced in real time. Those systems require communications networks to function. Water treatment facilities use digital monitoring and control systems. Supply chain logistics run on digital inventory management, routing software, and communication between drivers, dispatchers, warehouses, and retailers. Financial transactions that pay for goods and services are digital. Emergency services coordinate digitally. At first, this seems like a standard observation about modern technology. Of course, things use computers. But the dependency here is more brittle than it appears, because digital infrastructure has its own specific vulnerabilities that differ fundamentally from those of physical infrastructure. Physical infrastructure typically fails gradually under stress. Pipes corrode, wires degrade, equipment wears out in ways that are observable and predictable. Digital infrastructure can fail suddenly and non-linearly. A software vulnerability can be exploited at scale across many systems simultaneously. A fiber optic cable severed at a key interchange can disrupt communications for millions of users within milliseconds. The internet was originally designed with resilience in mind. Traffic is supposed to route around failures automatically. That design philosophy holds true for the broader network architecture. But specific dependencies within that architecture are not equally distributed. Certain physical nodes, undersea cable landing stations, major internet exchange points, large data centers, carry disproportionate amounts of traffic. Disruption at those points has asymmetric effects. Cloud computing has concentrated enormous amounts of critical data and processing in a relatively small number of physical data center clusters operated by a handful of large technology companies. This concentration has produced real efficiencies. It has also produced real systemic risk. A major failure at a significant cloud provider affects not just that company's direct customers, but every service those customers provide to the wider public. Zoom out for a moment from the technical details and look at the behavioral dimension. Modern financial systems, banking, payments, credit, are entirely digital and entirely dependent on continuous communication infrastructure. People do not keep significant amounts of physical cash. Businesses do not hold large reserves of currency on premises. Transactions happen electronically, verified against cloud-hosted records, cleared through digital interbank networks. A serious disruption to digital communications does not just create logistical problems. It creates a financial trust problem. If transactions cannot be verified, commerce slows. If commerce slows, the supply chain slows. If the supply chain slows, the stress on energy and water systems increases. The cascade, again, moves through all four systems simultaneously. This is the underlying architecture of vulnerability that most people never think about, and that most policy discussions address incompletely. The four systems are not separate silos with separate vulnerabilities. They are a tightly coupled network where pressure in one domain transmits into all others. Understanding this architecture changes how one thinks about resilience and preparation, both at the individual level and the societal level. It shifts the question from what happens if the lights go out to how do systems under stress behave, and what determines whether they recover or collapse further. Now look at a realistic near-future scenario. Not a catastrophic one, not a science fiction event. Just a plausible convergence of stresses that falls within historical ranges of what has happened before. Consider a severe heat event, the kind that climate data suggests will become more frequent in coming decades, lasting 3 to 4 weeks across a large continental region. Not unprecedented, Europe experienced such an event in 2003. The American Southwest has experienced multi-week extreme heat events in recent years. The heat event immediately increases electricity demand as air conditioning loads rise. Grid operators manage demand through rolling brownouts. Some transmission equipment operates near its thermal limits. In several locations, equipment fails under the sustained load. A partial cascade begins. Several million people lose power across a multi-day period. Without power, water treatment and pumping systems begin transitioning to emergency generation. Fuel for those generators begins moving through logistics chains. The heat slows truck driver availability. Regulations limit driving hours, and heat-related illness affects logistics workers. Fuel resupply to generators slows modestly. Some water treatment facilities reduce output to conserve fuel. Meanwhile, the heat increases mortality among elderly populations, increasing demand on healthcare systems. Healthcare systems are already managing increased patient load from heat-related illness. Hospitals operating on emergency generation are managing carefully. In agricultural regions, irrigation systems stressed by heat and reduced power availability produce suboptimal results during a critical growing window. The effects on harvest won't be visible for weeks, but the trajectory has already been set. Communication systems remain functional in most areas, but in regions with power outages, cellular towers deplete their battery backups after several hours and go offline. Digital communications in affected areas degrade. Emergency coordination becomes more difficult. At first, this seems like a regional emergency with containable consequences. Most people focus on the obvious impact: displaced people, power company response, utility repairs. The story in the news is about the heat and the power companies. But zoom out for a moment. The full cost of this scenario, calculated not over days, but over 6 months, includes agricultural shortfall effects on food prices, healthcare costs from illness and mortality during the event, economic productivity losses from disrupted business operations, insurance claims, and infrastructure repair costs, and the downstream effects on supply chains of the logistics slowdown during the peak stress period. None of these secondary effects are dramatic in isolation. Together, they represent a significant drag on economic stability in the affected region. And similar events, in different forms, are happening with increasing frequency across different regions of the world simultaneously. This is the real challenge of the four infrastructure systems in the coming decades. It is not one catastrophic failure. It is the cumulative stress of many moderate failures, each individually manageable, together adding up to a structural strain that systems were not designed to absorb indefinitely. The global dimension of this matters. Supply chains connect economies across continents. A disruption in food production in one major agricultural region affects food prices globally. A disruption in semiconductor manufacturing in one concentrated geographic area, as the pandemic years demonstrated, affects production of goods, ranging from automobiles to appliances to medical equipment worldwide. Zoom out further and consider that the four systems described here were built primarily in the 20th century, when assumptions about climate stability, geopolitical order, and population distribution were different from what they are now. The infrastructure was designed for a set of conditions that is changing. Electrical grids designed for predictable, centralized generation are adapting, slowly and with significant friction, to a more distributed, variable generation landscape driven by renewable sources. That transition is real and important, but it involves its own transition risks and vulnerabilities during the adaptation period. Water infrastructure in many older urban systems is aging significantly. In the United States, the American Society of Civil Engineers has consistently rated water infrastructure at a C or C- level, not failing, but aging and underfunded relative to what maintenance and replacement would require. The average water main in many American cities was installed decades ago. Supply chain systems are slowly adjusting after the disruptions of the early 2020s, with some movement toward more regionalized production and higher strategic inventory levels for critical goods. But the efficiency pressures that drove just-in-time optimization in the first place have not disappeared. Economic incentives still push systems toward leanness, which is another word for low redundancy. Digital infrastructure is expanding rapidly and in many ways becoming more capable and more redundant at the network architecture level. But the concentration of critical services in a small number of cloud providers and the increasing sophistication of state-level cyber operations means that the risk profile of this system is not simply declining with investment. What does all of this mean for how societies and individuals should think about infrastructure? The honest answer is that it means accepting a more realistic model of how dependent modern life actually is on these four systems. Not to generate fear, but to inform genuine resilience thinking. Resilience is not about returning to a pre-industrial state. It is not about individual self-sufficiency as a substitute for collective infrastructure. Those approaches confuse the scale of the problem. The four systems that hold civilization together are systems. They require collective management, investment, and planning. What genuine resilience looks like in practice is investment in redundancy, even when redundancy is economically inefficient in the short term. It looks like strategic reserves of fuel, of water treatment chemicals, of critical medicines and food commodities, held by governments or regional authorities as insurance against disruption. It looks like cross-sector planning that treats the four systems as the interconnected network they actually are, rather than managing each in isolation. At the individual and community level, resilience means understanding one's own dependency on each of these systems clearly enough to know which ones are most likely to experience stress in a given geography and what reasonable contingency looks like. Not prepping for the end of the world, but preparing thoughtfully for the disruptions that historical data suggests are likely over a 10 or 20-year window. The four systems, energy, water, supply chains, and digital communications, are not fragile in the sense of being poorly designed. They are fragile in the sense that all tightly optimized, highly interconnected systems are fragile. They are efficient under expected conditions and stressed by conditions outside those expectations. The conditions outside those expectations are occurring with increasing frequency. That is not a reason for despair. It is a reason for clear-eyed analysis and deliberate adaptation, which is, historically, what human societies do when they choose to do it well. Civilization is not held together by governments or laws or money, though all of these matter. It is held together by electricity moving through wires, water moving through pipes, goods moving through logistics networks, and information moving through communication systems. These are the real foundations. And foundations, by their nature, require maintenance. Not occasionally, not when a crisis forces the issue, but continuously, as a basic commitment to the functioning of everything built on top of them. That is, perhaps, the most important thing to understand about the four systems that hold civilization together. They do not maintain themselves. There is a tendency, when discussing infrastructure at this scale, to assume that the people responsible for managing these systems understand their interdependencies fully and are planning accordingly. In some cases, that is true. In many cases, it is not. Not because planners are incompetent, but because the four systems have historically been managed by entirely separate institutions, agencies, and industries with little formal coordination between them. An energy regulator focuses on the grid. A water authority focuses on pipes and treatment. A logistics ministry focuses on roads and freight. A telecommunications agency focuses on spectrum and networks. The connections between these domains are rarely anyone's primary responsibility. This institutional fragmentation is one of the quieter risks in the infrastructure picture. When a stress event crosses multiple systems simultaneously, as most serious disruptions do, the response tends to be slower than it would be if those systems were managed as a unified network. Each agency waits for information from the others. Jurisdictional questions slow decision-making. Resources that could move efficiently across domains instead move through bureaucratic channels at a pace that the situation does not afford. The 2003 Northeast blackout investigation later found that communication failures between utility operators, not just technical failures, were central to how the cascade progressed as far as it did. The human coordination layer matters as much as the physical infrastructure layer. Investment in these systems also follows a political logic that does not always align with engineering logic. Infrastructure spending is expensive, the benefits are diffuse and long-term, and the consequences of underinvestment are typically invisible until something breaks. Replacing an aging water main is not a visible achievement. A ribbon cutting at a new facility is. This asymmetry between the political reward for building new things and the political cost of maintaining existing ones has produced, in many countries, a pattern of underinvestment in maintenance relative to what the systems actually require. The result accumulates quietly over decades until a pipe bursts under a city street, a transmission tower fails in a windstorm, or a bridge closes unexpectedly. At that moment, what looked like a sudden failure reveals itself as the predictable outcome of a long and visible trend. Public understanding of these systems also matters in ways that are practical rather than merely academic. Societies that broadly understand how their infrastructure works, where their water comes from, how their grid is balanced, what makes supply chains vulnerable, tend to support the policy decisions and investment levels required to maintain those systems. Societies that treat infrastructure as background noise, as something that simply works and requires no particular attention, tend to underinvest until a crisis forces a reckoning. The reckoning is usually more expensive than the maintenance would have been. It is also less orderly because it happens under stress rather than under stable planning conditions. Public literacy about infrastructure is, in this sense, not a technical matter, but a civic one. None of this is cause for paralysis or pessimism. The four systems described here have been built, maintained, and improved by human effort over generations, and that effort is ongoing. Engineers are designing smarter grids. Urban water planners are implementing better leak detection and pipe replacement programs. Supply chain strategists are building more geographic diversity into critical production networks. Digital infrastructure is expanding its redundancy at the architecture level even as new vulnerabilities emerge. Adaptation is already happening. The question is whether it is happening at a pace and scale that matches the rate at which stresses are accumulating, and whether the people making the decisions that determine that pace have a clear enough picture of the interconnected system they are managing. That picture, examined honestly and without illusion, is what this analysis has attempted to provide. And that is where we leave this. Not with a warning and not with reassurance, but with a clearer view of the four systems that make modern life possible. Their logic, their vulnerabilities, their interdependencies, and the human choices that will determine whether they continue to hold. The grid, the pipes, the supply routes, the data lines, they are older than most people think about them, more fragile in specific ways than most people assume, and more worth understanding than almost anything else that shapes the daily texture of civilized life. Thank you for watching.